All right. So today is like a Thursday, could be a Friday or a Thursday, not too sure. But let's get started on trigonometric ratios of angles from 0 to 360. Now, this is the first lesson of trigonometry. And generally speaking, people think trigonometry is the study of triangles. Yeah, sure, and it is, and that's where we start, and we do some abstraction, and then all of a sudden trigonometry becomes the study of angles. And yeah, I guess it is. I definitely. And later on, what we'll discover is that trigonometry can also be the study of waves and circular motion. And this ends up being really important for the physical sciences. What travels in waves? Light, water travels in waves. And also the height on a Ferris wheel, if you trace the height with respect to time, that also creates a wave pattern as well. So anything that moves in a circle or travels in a wave, we can really model well with trigonometry. But let's start off with trigonometric ratios, the angles from 0 to 360. The previous knowledge that I expect you to know is SOHCAHTOA. Sine is equal to opposite over hypotenuse. Cosine is equal to adjacent over hypotenuse. Tangent is equal to opposite over adjacent. And I hope to be building a mountain out of that molehill. So here we are. I'm going to start off with some very nice definitions. An angle is in standard position if its first side, called the initial arm, is a ray from the origin along the positive x-axis. So allow me to draw that for you. This is called the initial arm. So this is what is required for angle in standard position. The second side, called the terminal arm, is a ray from the origin, any ray from the origin. Okay, so that makes sense. An angle is measured from the initial arm to the terminal arm. So allow me to go to this first example, Quadrant One Angle. This is my initial arm. My terminal arm has to terminate in quadrant number 1. And by definition, you're likely looking at that and you're saying that this makes an angle. If you were to estimate this angle, you might estimate it at 47 degrees or 63. I think that's probably going to be 67. But anyways, this is my angle theta. So in relation to this definition above, I'm going to say we have a positive ray along, or we have a ray along the positive x-axis that starts at the origin. We have a terminal arm that starts at the origin and goes away from the x-axis. The angle, if it's measured in a counterclockwise direction, or sometimes called anti-clockwise direction, the angle is positive. So if we measure from here to here, it is considered a positive angle. If it's measured from here to here, it is a negative angle. So a quadrant one angle from 0 to 90 degrees, I would draw it like this. What is that angle? I'm not too sure, nor do I care. All right, let's look what a quadrant two angle looks like in standard position. Again, we have our initial arm, which starts at our origin right there. And a quadrant two angle looks something like this. So really, we're measuring, if it was measured in a positive direction, we'd start at the initial arm and we'd go with the terminal arm. Quadrant number 3. Again, we start off with the initial arm. The initial arm starts at the origin. The terminal arm starts at the origin, and if it goes into quadrant 3, it's going to be like that. It goes off into quadrant number 3. So this angle would be measured like from the initial arm all the way to the terminal arm. So there's our theta there. Quadrant 4 angle. There's my initial arm. There's my terminal arm. And if it's a positive angle, it's going to be measured. Ooh, wrong writing tool there, sorry. It is going to be measured starting from the initial arm, going counterclockwise right there. There's my angle. So what we can see is quadrant 1 angles look like this. And if it's positive, what word would you attach to this? So this is quadrant 1 up here. Right, this whole quadrant. All quadrant 1 angles are known as acute angles. So if we measure from our initial arm to our terminal arm in quadrant number 2, this is quadrant number 2, these are known as obtuse angles. Now, I'm just trying to get you to access what you already know. We won't be using these terms very often, though. Quadrant 3 is the one way down here, if you recall. And here's quadrant 4. So, I hope that this helps. So, if you notice, I didn't mention anything about negative angles because I don't want you to confuse you. But, I mean, negative angles would just be starting from the initial arm here and going the other way. That's all. All right. Definition. An angle is in standard position and P of x is any point on the terminal side of theta. Then, by the Pythagorean theorem, r is equal to x squared plus y squared. Take the square root of that. Hence, r is greater than 0, or r is always positive. This definition is going to need a picture. Allow me to make a picture for you. Right, I made a picture to represent this, but yet I've defined really what r is. But angle theta, here's theta, is in standard position. So we can take the initial arm and we can measure it to the terminal. The way that I drew the terminal is terminates in quadrant number 1, although it's not necessary. So Pxy is a point that is on the terminal side of theta. Then, by the Pythagorean theorem, r is equal to the square root of x squared plus y squared. So r is what we call the radius vector. And often it is denoted by the absolute value of r, simply because r is always going to be positive given by the formula. So I'll show you what r really is. R is the distance between the origin and this terminal and this point. So I'm just going to make a picture of this. And if you notice, I created a right angle triangle with the closest x-axis. What we know is how long is, I made a triangle, how long is my triangle here? Well, that would be x long, right? How high is this triangle? Y. And this is 0, 0. If I go to point xy, I can go over x units, up y units. Then how long or how big is this radius vector? Now the radius vector is the distance from the origin to that point. In other words, it's just the hypotenuse, the length of the hypotenuse, but we call it the radius vector now. And the radius vector is equal to the square root of x squared plus y squared. That's just a definition. So let's continue on. Oh my God, this is the gift that keeps on giving, right? The basic 3 trigonometric ratios. There we have it. Sine, cosine, and tangent. You know these well. Some of you may even have tattoos of this on your arm. If P of x is any point, I'm going to start reading here. If P of x is any point on the terminal arm of an angle in standard position, then it can be shown that cosine theta is equal to the x-coordinate divided by my radius vector. Sine theta is equal to my y-coordinate divided by my radius vector. And tangent theta is my y-coordinate divided by my x-coordinate. So I am going to stop right here. This video is going to stop at this red line, but I feel like I need to do some explaining here. And I'm going to try to explain it using this picture. If we look at our triangle, and this is theta, if I were to label this with respect to theta, right? My r would be my hypotenuse. With respect to theta, x is my adjacent. With respect to theta, my y is my opposite. So if you wanted to calculate the sine of theta, it would be y opposite over my hypotenuse divided by my radius vector r. Cosine would be the adjacent x divided by my radius vector r. You with me? Tangent. Well, it's opposite over adjacent. It's y over x. Now, you may recall from last year, also, what does tangent measure? Now, this is just sort of a nice gift that is in trigonometry. Tangent is a measurement of the slope of the terminal arm. That is a handy little fact that we will come back to know more. But regardless, I said I'd stop the video at red. Hopefully everything up until now makes sense. If this is your first time encountering it, it is like I'm defining a new branch of mathematics. Really drawing on some basic knowledge, but then I created this whole world of angles in standard position and defined cosine, sine, and tangent. But stick with it.